The steel production process at BGH starts with melting iron in high-temperature furnaces. Molten steel is then transferred into ladles and poured into molds for casting. The molten steel radiates significant heat, so workers must maintain a safe distance and wear protective gear. After casting, the steel undergoes mechanical processing, such as drilling, grinding, and testing using specialized machines. Hot and heavy parts, weighing up to 50 tons, are transported by cranes, requiring strict safety measures. In the forging section, parts are heated to the required temperature before being shaped. Following forging, parts are immersed in quenching tanks containing cooling liquids. Throughout the process, strict safety protocols are enforced, including wearing helmets, protective footwear, and avoiding close proximity to moving equipment or hot surfaces. Machines are equipped with safety enclosures, and caution is needed in areas with slippery floors. The wheel is first cast into shape, then undergoes Maxion's reduced rim technology, where structurally unnecessary material is removed from the rim and backside. This reduces rim thickness to 2.15 millimeters, lowering weight while maintaining strength, styling, and performance standards. The production of hydraulic cylinders and valves at Servi involves advanced CNC machining and multitasking centers like the Mazak Integrex. Valve blocks are produced using automated flexible manufacturing systems, with over 1,000 tools to handle complex cavities. Deburring, including thermal deburring, removes machining residues. Surface treatments are applied in-house before oil contact to ensure durability. Cylinders are welded using submerged arc techniques, then assembled, pressure tested, and function tested. Products undergo cleanliness control and particle counting to meet offshore and class society standards. Simulation tools ensure designs are tested virtually before production, enabling efficient and high-quality manufacturing tailored to customer needs. The investment casting process at Reimer begins with creating and CNC machining of a die. Wax is then injected into the die to form precise patterns. These wax patterns are assembled onto trees for robotic dipping. The trees are repeatedly dipped in ceramic slurry and dried to form a strong mold. After shell building, the wax is melted out, and molds are stored to minimize damage. Before casting, alloys are analyzed using a Bruker Q2 to ensure correct chemistry. Molten metal is poured into the molds and allowed to cool. Castings are removed using pneumatic tools, then cleaned, ground, and inspected. Final machining operations are completed in-house to meet customer specifications. The engine block casting process starts with melting aluminum ingots in a high-temperature furnace until they become liquid. This molten aluminum is then transferred to a holding furnace, where it is maintained at the proper temperature before casting. Using high-pressure die casting technology, the molten aluminum is rapidly injected into a steel mold die at high speed, and pressure typically ranging from 100 to 200 megapascals. This high-pressure injection ensures that the aluminum completely fills even the most complex cavities of the engine block mold, resulting in precise and dense castings with minimal porosity. Once the mold is filled, the aluminum is allowed to cool and solidify under continuous pressure to maintain dimensional accuracy. After solidification, the mold opens, and the cast engine block is ejected by ejector pins. Excess material such as runners and flash is removed through trimming. The cast block is then moved to the machining stage, where critical surfaces and holes are milled, drilled, and finished to meet tight tolerances. This process enables the mass production of strong, lightweight, and dimensionally consistent engine blocks, making it ideal for modern automotive manufacturing. Engineers design valves using advanced 3D software. Patterns are made for sand molds, then cast with special alloys. CNC machines precisely machine valve parts. Components are coated, assembled, and integrated with electronic controls. Each valve undergoes strict inspection and pressure testing. Finally, valves are securely packaged and shipped worldwide. Cast steel valve manufacturing involves two main processes: investment casting for smaller parts and sand casting for larger components. The investment, lost wax method, begins with injecting molten wax into metal dies to form solid wax patterns of each valve component. These patterns are cleaned, marked with heat numbers for traceability, and assembled with gates and risers to ensure proper metal flow. The assembled wax structure is then coated with multiple layers, typically 7 to 9, of ceramic slurry and refractory materials, forming a hard shell. After curing, the molds are placed in a high-temperature dewaxing chamber, where the wax melts and is collected for reuse. The hollow ceramic molds are then baked in a furnace at up to 800 degrees Celsius to remove any residue and preheat the mold for metal pouring. Once ready, molten steel is poured into the preheated mold. After cooling, the ceramic shell is broken off and the casting is cleaned, cut, and inspected. For large valves, the sand casting process is used. A wooden pattern is placed into a flask and packed with bonded sand to form cope top and drag bottom halves. After curing and removing the pattern, the halves are assembled and molten steel is poured into the cavity. Once solidified and cooled, the sand mold is broken and the casting is cleaned. In both processes, the raw castings undergo grinding, blasting, and heat treatment. Dimensional and visual inspections are performed. Machine components are washed, assembled, and hydro-tested. Inspectors and operators stamp their IDs on each valve. Finally, the valves are primed, painted, serialized, and staged for delivery to customers or further machining. The manufacturing process of the 52 top entry trunnion ball valve includes precise assembly of the valve body and internal components tailored to API 6D standards. After mounting the bonnet, inline trim inspection and internal adjustments are performed using special tools. The valve undergoes thorough safety, sealing, and corrosion resistance testing under high and low pressure. Finally, the valve is packed and shipped for pipeline installation in the UAE, meeting strict customer specifications. Cold wound coil springs are conveyed through precisely controlled ovens, uniformly heated to 600 to 900 degrees Fahrenheit, held at peak temperature, then gradually cooled to room temperature, effectively relieving residual internal stresses. The hot wound spring process involves heating steel rods in a walking beam furnace, coiling them into shape, and then quenching and tempering the coils, followed by grinding and shot peening for finish. The investment casting process begins with the creation of a wax pattern by injecting wax into a metal tool and die. Since the early 90s, 3D printing technology has been used to produce rapid prototype castings. The wax patterns are then assembled onto a wax tree or sprue, with gates connecting them. This structure ensures molten metal flows properly during casting. Next, the wax tree is dipped into a ceramic slurry to form a mold, which is repeatedly coated with fine sand or stucco. After drying, the mold is heated to remove the wax, leaving a hollow ceramic shell. The mold is preheated before molten metal is poured in. Once cooled, the shell is removed, and the castings are separated from the sprue. Finally, the finished castings are ground, polished, and undergo any necessary machining. Cold winding begins by feeding high-tensile wire through rollers and fulcrum pins, wrapping it around a fixed mandrel to form coils. Hot winding starts by heating steel bars to 1,750 degrees Fahrenheit in a walking beam furnace, then coiling them around a mandrel. The hot coil is quenched in oil and tempered. Both methods are followed by grinding and shot peening to enhance strength, precision, and fatigue resistance for various applications. Corte Circulos employs specialized machining and automation processes to produce precise circular cuts in metal components. The process begins with loading metal sheets into automated feeders, which position the material accurately. Next, CNC-controlled cutting machines, using plasma cutters, execute the circular cuts based on pre-programmed designs. These machines operate with high precision, often achieving tolerances of plus or minus 0.1 millimeters. Post-cutting, the components undergo quality inspections to ensure they meet specified standards. Stainless steel tank production begins with cutting and shaping AISI 304 and 316L steel sheets. These sheets are rolled and welded to form cylindrical bodies and conical bottoms, produced in-house up to 5,000 millimeters diameter. Welds are polished to achieve surface roughness up to 0.8 micrometers raw. Tanks are then fitted with agitation systems, heating or cooling jackets, for pasteurization, fermentation, or storage, and accessories like manholes and valves. Units such as long pasteurization baths, fermentation tanks, cream tanks, and CIP vessels are assembled per specific dairy processes. Final steps include hydraulic testing, surface treatment, and quality control to ensure hygiene and compliance. Each tank is customized to suit processes like curd production, whey processing, or mixed maturation. IBOC processes over 4,000 variants of spring steel wire. Springs are formed either by CNC-controlled winding of pre-tempered wire up to 26 millimeters, or by mandrel coiling of thicker wire up to 55 millimeters, followed by heat treatment. After forming, the springs are stress-relieved, ends are ground and deburred, and the entire surface is shot peened for fatigue resistance. The springs are then compressed to solid height, inspected, and coated with epoxy for corrosion protection. The sand casting process for a race car cylinder head begins with creating a metal pattern and sand cores to form internal cavities. These are placed in a flask and packed with sand mixed with a binder to form the mold. Molten aluminum is then poured into the mold cavity. After cooling and solidification, the sand mold is broken away in the shakeout process. The rough casting is cleaned to remove residual sand and imperfections. Finally, the casting undergoes precision machining to achieve the required specifications and surface finishes for use in high-performance engines. The production process for manufacturing domes and torr-spherical caps involves several steps. First, specialized cutting is done using CNC plasma pantograph for straight and shaped cuts. The material is then bent using a press brake to form angles. The final step includes rolling with a rolling machine to achieve curved shapes. The production of the tank shell begins with flattening steel plates of 6 mm and 8 mm thickness, designated for forming cylindrical sections with a diameter of 3,200 mm. These plates are fed into a plate rolling machine, where they are bent into curved segments. Precise calibration is performed to ensure the correct diameter and alignment. After forming, the cylindrical shells are tack welded at the seam and then subjected to full circumferential welding using submerged arc welding for deep penetration and uniform strength. Next, the shells undergo surface grinding to remove welding slag and prepare for inspection. Non-destructive testing, such as ultrasonic testing, is performed to verify weld integrity. Once approved, lifting lugs are temporarily attached to facilitate vertical assembly. The cylindrical sections are aligned and joined vertically. Accurate fit-up is achieved with alignment tools and internal scaffolding. Each circumferential weld between sections is executed, followed by grinding and testing. After the shell is fully assembled, it is lifted and positioned for further processing, such as nozzle installation and painting. Throughout the process, dimensional accuracy and weld quality are continuously monitored to meet tank design specifications. The CNC electronic tube bending machine bends sectional garage door springs with high precision, allowing for fixed and variable radii, overlapping bends, and automatic tool changes in a single cycle. Itesai designs and manufactures complete ammunition production lines, integrating high-capacity machines like lead wire extrusion, case presses, core presses, and loading units. All machinery is modular, assembled in-house, and verified with optical or mechanical inspection for zero defects. Using carbide tooling from its own factory, Iteshi produces equipment for any caliber. It also offers factory setup, modernization, ERP integration, and remote support. Every project includes operator training, spare parts, and performance monitoring systems. Brass cups are fed into the vertical H-type case press, where they undergo multiple forming steps to become non-grooved 9 by 19 mm cartridge cases. The process includes drawing, length cutting, and firehole piercing, followed by tapering and necking in sequence. With an 8-guide slide system, the machine maintains high precision even under stress. Controlled by a PLC and monitored via a touch LCD screen, the press operates fully automatically. It features recirculated oil lubrication and mold cooling. For pistol calibers, the press runs at 20 RPM with a 75-ton capacity and 6 kilowatts power. Pneumatic clutch brake and safety guards ensure reliable and safe performance. The production process of monoblock aluminum aerosol cans begins with feeding round aluminum blanks into the lubrication drum, where they are lubricated, separated, and aligned. These blanks are then forwarded to the extrusion press. Using a punch with up to 400 tons of force, the press transforms each blank into a cylinder by plastically deforming the aluminum and forcing it to flow backward along the punch wall. Next, the cylinders enter the ironing machine, which reduces wall thickness and forms the base of the can. This step ensures mechanical strength and material efficiency. The MHB trimming and brushing machine then cuts each can to the exact required length and removes sharp edges. The cans are also surface finished using rotating brushes to create a uniform matte appearance. A pickup system transfers the cans onto a pin chain conveyor, which moves them to the washer. The cans are washed using 80 degrees Celsius water and detergent in a cascade system to remove any residual oil and particles. They are then thoroughly dried inside and outside in a dryer powered by gas or electricity. To maintain continuous production, an accumulator temporarily stores cans and synchronizes machine speeds. The cans then move to the inside spray machine, where spray lances enter and coat the internal surfaces with protective lacquer to prevent corrosion. After drying, the cans are sent to a pair of flex store accumulators that buffer the flow before and after decoration. In the decoration section, the base coater applies a primer layer. Then, the printing unit adds up to 9 colors with high precision, followed by an over-varnish layer for protection and visual gloss. Cans are dried again in curing ovens. In the necker, the cylindrical bodies are necked and curled to form the can opening. Leak detectors inspect each can for micro leaks before flawless units are packed for delivery. The AIM 4000 CNC spring coiling machine begins by feeding wire through 4 servo-driven rollers with 50,000 pounds of hydraulic clamping force. The wire is precisely positioned by 6 servo-controlled axes, enabling 3D movement of the coiling point. The machine forms compression, torsion, or wire forms using single-point coiling. The point axis adjusts initial tension and leg bends. A servo-driven cutter trims the spring at top dead center. All operations are controlled via a Windows-based CNC interface, allowing quick setup, automatic tool positioning, and 10-minute part changeovers. The shotgun shell loading machine loads shells with lead shot, steel shot, buckshot, or slugs. It handles cases from 50 mm to 90 mm, using a single transport line. The centerfire loading machine assembles primed cases, gunpowder, and cartridge cases with rotary motion. It operates at double production for pistol calibers and single for medium calibers, driven by servo motors and pneumatic components. After each operation, check stations ensure quality control. The primer inserting machine inserts primers into cartridge cases continuously with a cam-driven system. The shot casting machine produces highly spherical lead shot by melting lead with gas, fuel oil, or electricity, ensuring energy efficiency. The lead wire extrusion machine melts and molds lead into billets. The buck machine cold presses lead wire into buckshot. The lead core press shapes lead into bullets. Finally, the bullet jacketing machine, double action press, resize machine and trimming machine shape, resize, and finish bullets to precise specifications. The production of a Torino alloy wire wheel rim begins with cutting the appropriate length from a 5-meter long, thick wall 5000 series aluminum tube using a bandsaw. This initial cut produces a rough edge, which is then precisely turned on a lathe to square the ends and create a smooth surface. This step is essential to prevent cracks during pressing, as any surface imperfection could cause the tube to split under pressure. Once the ends are machined, the tube is placed in a 200-ton hydraulic press. It is shaped using a purpose-built plug designed specifically for each rim diameter. The shaping ensures the tube can be securely held in a clamshell tooling, also custom-made for each rim size to prepare it for spinning. After pressing both sides and verifying the fit, the partially formed rim is sent to Sapphire Spinning Limited. At Sapphire, the rim is heated and spun on a CNC spinning machine. Using multiple passes of a spinning roller with lubrication and controlled heat, the aluminum is gradually formed into the precise profile required for the tire side of the rim. When complete, the rim returns to Torino's workshop for further refinement. Back at the machine shop, the rim undergoes additional shaping on a large lathe, especially on the inside surface. This process adjusts wall thickness and fine-tunes the profile to meet structural and aesthetic requirements. If a polished finish is specified, the rim is hand-sanded using increasingly fine grits, then polished with progressively softer grit mops. This multi-step process reveals a mirror-like shine, reflecting the high craftsmanship involved. After polishing, the rim is marked according to the spoke layout. For a 72-spoke wheel, dimples are pressed and holes are drilled in precise rows at calculated angles. Custom tooling ensures each hole follows the radius of its dimple. The rim is then deburred both mechanically and by hand. Each spoke is cut, bent, and threaded using a rolling machine for added strength. Assembly proceeds row by row, with spokes tensioned and the wheel trued on a precision jig. Final offset and alignment are verified, and the rim is stamped with a job number before being carefully packaged for shipment. A heated steel ingot is transported by crane to a hydraulic forging press. The press shapes the ingot through repeated compressions, gradually reducing its cross-section and elongating it. Between press cycles, the ingot is rotated or repositioned to ensure uniform shaping. A manipulator assists in precise handling and alignment. The material flows freely since no closed mold confines it. For larger parts, additional heating in a furnace may be required to maintain forging temperature. Once the desired dimensions and structure are achieved, the forged piece is allowed to cool gradually, completing the free forging process. The process of manufacturing and assembling steel mill frames begins with the cutting of raw billets. The billets are transported and precisely placed by a high-tech MEN robot, ensuring accurate handling. The billets are then automatically loaded from the billet storage area into a ring rotary furnace designed by IOV, where they are heated to the necessary temperature. Once the billets are heated, they are automatically unloaded from the rotary furnace using an automated system. The modern forging process is designed to preserve the internal structure of the material, which is critical for producing high-quality bearing rings. This process ensures that the bearing products exhibit superior quality and extended service life. The entire operation is largely automated, with 3 industrial robots performing the majority of labor-intensive tasks. The first robot feeds the billets into the system. The second robot places the billets onto the ring rolling mill, and the third robot handles the stacking of the finished components. The final stage of the process involves the rolling of the heated billets into bearing rings using a specialized ring rolling machine. This step shapes the billets with precision, ensuring the components meet strict quality standards. Plastic models are 3D printed by voxeljet using a binder jetting process. After printing, they are hardened, cleaned, and inspected. Wax is applied to seal the surface before manual and robotic ceramic coating. The models are burned out in a kiln, leaving a cavity inside the ceramic shell. Molten metal is poured into the mold to form the part. Once cooled, the ceramic shell is broken, and gating systems are removed. Final steps include deburring, surface repair, and inspection. This efficient process allows rapid production of complex castings from digital designs. The production of rolling mill rolls in Siegerland is a highly specialized process combining traditional craftsmanship with modern industrial techniques, ensuring durability, hardness, and precision. The process begins with mold preparation, a critical step that determines the roll's quality. Skilled workers construct the mold by hand, starting with the lower mold box, which is placed in a sandpit to support the weight of both the mold and the molten metal. A core, crafted from hardened sand on specialized machines, is meticulously inserted to form the roll's internal structure. This core is essential for high rolls, whether cast as solid rolls or with attached journals. The multi-part mold is then carefully aligned and secured to ensure uniformity and prevent defects during casting. Next, the molten metal is prepared in advanced furnaces designed to produce a highly homogeneous melt. Before casting, metallurgical samples are taken from the melt to verify its chemical composition and suitability for the roll's intended application. Additives are introduced to tailor the material's properties, such as hardness and toughness, to specific requirements. Once the batch is approved, the casting process begins. For most rolls, the static casting method is used, where molten metal is poured into the mold from the bottom through a tangential gating system. This allows the melt to flow in a controlled, circular motion, filling the mold evenly from bottom to top, minimizing turbulence and ensuring a pore-free surface and consistent internal structure. For large rolls, weighing up to 300 tons, the process is scaled up significantly. Multiple ladles pour molten metal simultaneously to meet the immense volume required, with up to 500 tons of melt used in a single cast. Alternatively, centrifugal casting is employed for certain high-performance rolls. In this method, the mold rotates at several hundred RPM, and the molten metal is poured into the spinning mold, adhering to the walls to form a hard outer shell. Once this shell cools, a softer core material is poured into the center, creating a roll with a tough exterior and resilient interior, ideal for demanding applications. After casting, The roll undergoes a prolonged cooling period, lasting 2 to 3 weeks for larger rolls, to ensure structural integrity. The mold is then removed, and residual sand is cleared. The raw roll is subjected to heat treatments in controlled ovens to enhance its mechanical properties. Machining follows, using advanced CNC-controlled lathes and grinders. The casting skin is turned off, and the surface is precision ground to achieve exceptional smoothness and dimensional accuracy within thousandths of a millimeter. Rigorous testing, including ultrasonic inspections, hardness measurements, and micrometer checks, ensures the roll meets strict standards for uniformity, hardness, and durability, making it ready for use in rolling mills worldwide. At Petter Spring Manufacturing, the process starts with cutting high-grade steel wire to precise lengths for each coil. The wire is then heated uniformly in a walking beam furnace at 900 degrees Celsius. After heating, the wire is fed into a CNC coil winding machine where it is hot wound into coils. The coils are then quenched in an oil bath to cool at a controlled rate. Following this, the coils are tempered in a gas-fired furnace, which ensures they retain their elasticity. If flat ends are needed, the coils are ground in a jig using a rotating grinding stone. The coils undergo shot peening in a large drum to relieve stress and clean the surface. Finally, the coils are tested for scragging and loaded ride height before being powder-coated, cured in an oven, and packaged for shipment. The production of Borbette's light alloy wheels begins by preheating the metal to 100 degrees Celsius, then melting it in a furnace at 750 degrees Celsius for 1 hour. Once cooled to 720 degrees Celsius, the molten alloy is stirred for uniformity and cast into molds made in-house using CNC milled cores. After casting, the wheel undergoes automated X-ray inspection to detect internal defects. It then passes through heat treatment and is machined in 3 steps, turning the back face, drilling holes, and turning the front face. Wheels are deburred, inspected, and test stamped before entering the paint shop. They are powder coated, baked, wet painted, and cured. Final quality checks include surface inspection and leak testing before packing and dispatch. The aluminum wheel production at Maxion Wheels, Pune includes melting, degassing, and chemistry analysis. Low-pressure die casting forms each wheel, followed by X-ray inspection and heat treatment. Fully automated machining ensures precision, verified by CMM and balance tests. Final steps include leak testing, painting, and diamond cut machining. The plant produces over 2 million wheels annually with high structural integrity. The cold winding process begins with pre-tempered wire fed through rollers and fulcrum pins, then coiled around a fixed mandrel to form springs. After coiling, the springs undergo precision grinding, shot peening, and finishing using advanced CNC coilers and grinders. Shot peening bombards springs with steel balls to reform metal structure, enhancing crack resistance. Typical shot size is 0.3 to 0.6 millimeters diameter. The hydraulic edge bending machine bends sheets from 2.75 millimeters to 6.35 millimeters thick, with a minimum radius of 5 millimeters and maximum of 50 millimeters. It handles stainless and carbon steel up to 8 millimeters thick. The machine forms flat and conical pieces with radii from 200 millimeters to 3,000 millimeters using hydraulic force. Parts undergo a 5-stage iron phosphate rinse, deionized baths, sealing, drying, electrostatic powder coating, then fast oven curing. Valve closes automatically via PLC vent valve closes, cylinder declamps, proxy switch activates, vent reopens, actuator completes closing cycle. The process begins by threading high-strength blank material into the line. The first external coil section is trimmed to remove irregular edges, and the system switches from dirty to clean rollers to prevent contamination. The coil sheet is homogenized to ensure consistent material properties. It then passes through a precision 17-roller straightener, which eliminates curvature and ensures a flat strip. A loop is created and adjusted to maintain proper tension between operations. The strip is fed forward using roll feed and guided into a 4-column swiveling shear for precise straight-edge blanking. The resulting rectangular blanks are stacked in neat piles. The strip undergoes cleaning using a combination of suction and compressed air to remove particles. A changeover is carried out to prepare for the next blank type. Trapezoidal blanks are also produced and stacked. This automated cut-to-length process ensures production efficiency for flat metal blanks. The aluminum hot strip rolling at CST begins with receiving and sequencing slabs, which are transported by overhead cranes to roller tables and then into a walking beam reheating furnace. After heating to around 1,200 degrees Celsius, oxide layers are removed, and slabs are rolled through roughing stands, including a vertical edger, reducing thickness to 20 to 40 millimeters. Slabs, now called transfer bars, are coiled in the coil box for thermal homogenization, uncoiled, trimmed, and finish rolled through 6 stands to final thicknesses of 12 to 16 millimeters. Strips are then cooled, surface inspected by cameras, hydraulically coiled, weighed, tagged, and sent for finishing or shipment. The production of forged steel components at Covarna Viva is a sophisticated, high-tech process. It begins with engineers designing the forging and its production technology using advanced 3D simulation software like NX, Forge, and Robot Studio. Tooling and dies are precisely manufactured on CNC machines using high-quality, heat-treated materials. The forging process is carried out on automated lines, processing a wide range of steels into parts weighing from 0.1 to 30 kilograms. Finishing includes heat treatment, shot blasting, and calibration with strict final inspection. Viva combines centuries-old forging principles with modern technology, ensuring precision, strength, and quality for the automotive and hydraulic industries. The process of raw material extraction begins with the use of surface mining, which replaces drilling and blasting. This method enhances safety and environmental sustainability. The surface miner cuts material directly, creating stable, well-drained excavation areas, reducing dust and noise emissions. It allows for optimal resource utilization, even near existing infrastructure. The machine's efficient design ensures high productivity and consistent material quality with minimal production costs. Through selective mining and quality control, material is extracted in the correct grain size, reducing the need for costly processing. The use of reliable machinery ensures continuous operation and cost-effective material transport. The GE Orge Slitting Line 1300 processes coils by first automatically transporting them to the decoiler. After uncoiling, the strip is precisely aligned and guided into the slitting shear, where up to 50 burr-free cuts are performed with minimal shaft deflection. The high-precision knife shaft bearings ensure accurate strip division, even for high-tensile materials. Tension is individually adjusted by pneumatic systems and a movable braking unit, enabling high winding accuracy without surface damage. Tool changes and setup times are minimized through automation, increasing throughput. The recoiler tightly winds slit strips, completing the efficient and continuous process with minimal power consumption. The automatic Y-shaped aerosol production line for spray paint begins with empty cans being fed onto the conveyor. They are aligned and sent to the valve insertion station, where valves are automatically placed. Next, the cans move to the gas filling unit, which injects propellant under pressure. Afterward, the spray paint is filled into the cans at the liquid filling station. Each can is then weighed to ensure accurate filling. Qualified cans proceed to the sealing and leak testing section. Once sealed, caps are automatically placed and pressed onto the cans. Finally, the finished spray paint cans are labeled, coated, and collected at the end of the line for packaging. The fully automatic production process of concrete blocks and interlock pavers using the COB 1842 machine starts with mixing raw materials and feeding them into the block-making unit. The COB 1842, the largest model of its series, then compresses the mixture into molds. Each pressing cycle produces 18 hollow or solid blocks, size 20 by 40 by 20 centimeters, or 42 interlock pavers. These freshly formed products are placed onto large pallets measuring 140 by 130 centimeters, made of either wood. After molding, the loaded pallet is automatically lifted by the elevator, which stacks pallets vertically. The finger car, controlled through the central PLC system, transports the stacked pallets from the elevator to the curing chambers. Its speed and movement are adjustable, allowing precise operation. Depending on the system setup, the finger car can handle 2x10, 1x14, or 1x15 layers per batch, with a maximum load of 10 tons. Inside the curing chamber, the products undergo a controlled curing process to ensure strength and durability. After curing, the finger car collects the pallets and transfers them to the lowerator, which unstacks the layers for the next handling stage. The entire factory, including the COB 1842 press, finger car, elevator, lowerator, and curing chambers, is operated automatically by a PLC control system. Forklifts are not used, since the large pallet size and lack of pallet legs make manual transport unsuitable.